Hey, Algebra 2, Lesson 12. We're talking about Ferris wheels again, but we're just going to use the Ferris wheels to model cyclical behavior. This lesson's going to be a little long, but the problem set isn't too bad. Okay, to start out, Ernesto thinks that this graph of f of x equals 4 sine x minus pi over 2. Danielle thinks it's the graph of f of x equals 4 times cosine x. Who is correct and why? It looks like our amplitude is 4, which makes sense because we are at a maximum of 4 and a minimum of 4. The sine always starts here, but if we're at x minus pi over 2, that means that we translated in that direction pi over 2, which you see right here by starting there instead of there. I went ahead and graphed the two equations. So here I have 4 sine times x minus 90. 90 is the same as pi over 2, which you guys know. And I graphed 4 sine x. So here we see the 4 sine x. We start at the origin, and then x minus 90. We start right here at pi over 2, which is 90 degrees, and go. I kept this graph here, which is in red, and then I graphed 4 cosine x. Okay, 4 cosine x is not the same. Okay, 4 cosine x starts at 4 and decreases, then increases. So no, they're not the same, but let me show you one more slide. Here we have 4 cosine x, which is in blue, and negative 4 cosine x, which is actually this graph. These two graphs are equal. They're laying on top of each other, so you can't tell the difference. But negative 4 cosine x and 4 sine x minus pi over 2 are the same thing. This one is a reflection over the x-axis. Alright, this will take a little while, but it's good, so we'll figure it out together. First of all, a carnival has a Ferris wheel that is 50 feet in diameter with 12 passenger cars. When viewed from the side where passengers board, the Ferris wheel rotates counterclockwise and makes 2 full turns each minute. Riders board the Ferris wheel from a platform that is 15 feet above the ground. We will use what we have learned about periodic functions to model the position of the passenger cars from different mathematical perspectives. We will use the points on the circle in the diagram on the right to represent the position of the cars on the wheel. Okay, let's see, 50 feet in diameter, 12 passenger cars, 15 feet above the ground, counterclockwise, 2 full turns each minute, just underlining the important stuff. I think that's it. Alright, for this exercise, we will consider the height of a passenger car to be the vertical displacement from the horizontal line through the center of the wheel. So right there. And the co-height of a passenger car to be the horizontal displacement from the vertical line through the center of the wheel. Let theta equal 0 represent the position of car 1 in the diagram above. Okay, that's theta equals 0. Our angle isn't anything, our angle's 0. Sketch the graphs of the co-height and the height of car 1 as functions of theta, the number of radians through which the car has rotated. So let's look at the height of the car, which I'm doing in blue right now. As we rotate around, let's just do 90 degrees or pi over 2. When car 1 is right there, we're at the maximum, which would be up at 25. So we're right there. As we continue to rotate around, we're right here. So pi over 2, pi, we're back at 0. Rotate around, 3 pi over 2, we're down at negative 25. And then at 2 pi, we're back at 0. So the height looks something like that. As we look at the co-height, which I'm going to do in black, we can take that car 1 up to the 90-degree mark, and we're at 0, our vertical distance. Sorry, over here at the 0 mark, we are at 25. So distance from here to there is 25. Okay, back at pi, so, yeah, pi, we are over here. We're at 25, negative 25 though. And then back at 0, and then back at positive 25. So our co-height looks something like that. Okay, I just recopied it. You see the book's answer here. It matches our answer. Yay! Let's move on. What is the amplitude of the height and co-height functions up the Ferris wheel? They're 25 for both. Okay, that was the maximum and minimum for both graphs. Let x of theta represent the co-height function after rotation by theta radians. Let y of theta represent the height function after rotation by theta radians. Write function x for the co-height and y for the height in terms of theta. So our x of theta, let's see, x was the co-height. If you remember, co-height, I don't have any room, looks like this. That is definitely a cosine function. So our amplitude is 25, and we have cosine of theta. Y of theta, that was our height. That one looked like this. That's a sine function. Graph the functions x and y from part C on a graphing calculator set to parametric mode. Use a viewing window and sketch the graph below. This took me a while to figure out. Hold on, I'm going to take a picture of my calculator. Okay, I would recommend you trying this on your own, just to see the circle form. It's sort of neat when you set your T-min. That T-min should be 0. Sorry. 0 to about 6.3 is one entire circle because we're in radians. So 57 degrees is 1 radian, 6.3 radians, and 360 degrees. So it just tells you that the circle is going to go 1 rotation. Okay, I needed my scale to be pretty small, or we get a lot of straight lines, like it starts to look like this. So I made the scale pretty small, but I think everything, yep, you see everything there. But please go ahead and try it. This right here is the parametric mode. You see I have radians. I think that's all the stuff that you need. It says it right here too. Yeah, so go ahead and try it. Pretty cool. Okay, E, why did we choose the symbols x and y to represent the height and co-height functions? If we didn't, we would only get half of our graph. So the co-height function measures the horizontal position of the passenger car that we typically name x. The height function measures the vertical position of the passenger car that we typically name y. It makes sense to use x as the name of the function that describes the horizontal movement, and y as the name of the function that describes the vertical movement. Evaluate x of 0 and y of 0 and explain their meaning in the context of the Ferris wheel. So if we're evaluating at 0, that's when the wheel hasn't rotated yet. Oh goodness, sorry about that. So our Ferris wheel our passenger car is still there. We have co-height and height, so when the wheel has not rotated yet, the co-height of the car is 25. So that's the distance from here to there. And the height of the car is 0. So it makes sense that our answers would be 25 and 0. I didn't close my parentheses there, but you don't need to. How about evaluate at pi over 2, which will be up here. Okay, 25 cosine of pi over 2 is going to be 0, and 25 sine of pi over 2 is going to be 25. Okay, our distance for cosine is from there to there. Our distance for sine, our height is 25, and our horizontal distance for cosine is 0, which makes sense. Crunch it in your calculator, and you're going to get the same answer. All right, next one. The model we created in exercise 1 measures the height of car 1 above the horizontal line through the center of the wheel. We now want to alter this model so it measures the height of car 1 above the ground. If we measure the height of car 1 above the ground instead of above the horizontal line through the center of the wheel, how will the functions x and y need to change? If I go back to the description of the problem, we are at 15 feet above the ground. It says that riders board the Ferris wheel from a platform that is 15 feet above the ground. So there's our distance there. If we measure, we did that. So how will the function x and y need to change? We can say that the co-height function x doesn't change because that's the horizontal distance. The height function y does in fact change, though. The height function is going to have to add 15 to it. Since car 1 starts 40 feet above the ground, so 25 plus 15 is 40 feet. So that whole distance is 40. Let theta equal 0 represent the position of car 1 in the diagram to the right. Sketch the graphs of the co-height and the height of car 1 as functions of the number of radians through which the car has rotated. Here we have co-height, and we said that it's not going to change, but height does in fact change. It looks like we are at 40. Okay? If we looked at our Ferris wheel, I think what I said earlier is actually incorrect. So there's our Ferris wheel. This first car is no longer, we're not measuring it from loading there, we're measuring it from loading at a platform 40 feet above the ground. This is 25 and this is 15. So that's where our 40 comes from. How are the graphs on part B related to the graphs from exercise 1A? I copied them just to show you the book's version of it, and hard to see, but that is at 40 and that is at 0. So we just did a shift vertically by 40 feet. The co-heights don't change. The only thing that changes is the height. From this perspective, find the equations for the functions x and y that model position of car 1 with respect to the number of radians the car has rotated. So x of theta is going to be the same, 25 cosine theta, and then y of theta equals 25 sine of theta. plus 40. Okay, change the viewing window on your calculator and graph the functions x and y together. Sketch the graph. Hold on a second, I will take some pictures of my calculator. Alright, there we go. I just changed the viewing window like it asked. I typed in plus 40 to the sine function and got the circle. It's pretty cool. Alright, evaluate x of 0 and y of 0 and explain their meaning in the context of the Ferris wheel. If we have x of 0, that's 25 cosine of 0. That gives us 25. That's our horizontal distance. And then y of 0, 25 sine of 0 plus 40 is 40, because that's our vertical distance. So when the wheel has not yet rotated, the co-height is 25 and the height is 40. This means the car is at the 3 o'clock position. Okay, how about evaluate pi over 2? So we're up here. Okay, our vertical position, so the y should give me an answer of 40, and the x should give me an answer of 0. So let's go ahead and calculate it. I'm going to write this here, though. Keep them in the same order. So x evaluated at pi over 2 is cosine pi over 2 is 25 cosine pi over 2 is 0. And then y, pi over 2, that's going to be 25 sine pi over 2 plus 40, which will give me 25 plus 40, which is 65. So that's my distance here. Alright, in reality, no one boards a Ferris wheel halfway up. Passengers board at the bottom of the wheel. To truly model the motion of a Ferris wheel, we need to start with passengers on the bottom of the wheel. Refer to the diagram below. We have car 1 down here now. It's sort of funny when they always talk to us about boarding over here. Like, that means the Ferris wheel either goes into the ground or you're climbing a lot of stairs to get up to the boarding platform. Not reality, but it's a good starting place when you're talking about trigonometric functions and graphs. So part A, let theta equals 0 represent the position of car 1 at the bottom of the wheel in the diagram above. Well, on the diagram of the previous slide. Sketch the graphs of the height and co-height of car 1 as functions of theta, the number of radians through which the car has rotated from the position at the bottom of the wheel. Our co-height, again, doesn't change. We're good, right? So when we start at the bottom of the wheel, we're starting down here. We start at 0, 0. We go up to 90 degrees. Our co-height is now 25. We go up to 180 degrees. Our co-height is back to 0. We go over to 3 pi over 2, and we're at negative 25. And then back to 0, and we're at 0. If we just look at height, we're starting here, but we are 15 feet above the ground. So that's why at theta equals 0, we're at 15. Here we're at 25 plus 15. There's our midline. That says midline. We're at 40. Up here we're at 50 plus 15. 65, back to the midline, back down. Pretty awesome. B, how are the graphs from part A related to the graphs from exercise 2B? Between those two graphs, we have a horizontal pi over 2 units to the right. So there is our the difference, how they're related. From this perspective, find the equations for the functions x and y that model the position of car 1 with respect to the number of radians the car has rotated. Hold on a second, I'm going to go grab those graphs and then we can look at it. Alright, they are a little bit small, but you should have them written on your paper also. If we look at x, which is our co-height, x of theta, we're still at an amplitude of 25 cosine, but as we said, we shifted pi over 2 to the right. And then our height, we still are at an amplitude of 25. With our sine function, we've got the same shift, but we are up. We have a vertical translation of 40. Pretty cool. Okay, if you graph them together on your calculator, that is what you will get. Go ahead and try it on your own. I'm not going to do it and take pictures again. And then evaluate x of 0 and y of 0. So for x of 0, remember that's our co-height. We're starting down here. So our co-height is our horizontal distance, and that's going to actually be 0. Y evaluated at 0, that's our height. So evaluated down here, our height is 15. Oh, I'm sorry, I see another error. Let's erase it before I forget. That should just be a 2. So if we crunch through the numbers, we'll get 15 here. Okay, I'm going to go ahead and test it on my calculator. Sorry, I just noticed an error. This should just be 0, not theta. Okay. And I usually test things out on my calculator because I just like to see the answer. Graphically, I see what I should get. I just want to make sure that I'm not crazy. So let's go ahead and try the next one. X evaluated at pi over 2 is 25 cosine pi over 2 minus pi over 2. Uh-oh. So here we're at this point. My co-height should be 25. And then y evaluated at pi over 2. Sine pi over 2 minus pi over 2. Okay, and my height should be 25 plus 15. I'm going to go ahead and type those in and double check that I'm not crazy. And, oh, sorry, I am crazy. Oh, for goodness sakes. Really, teaching very difficult Algebra 2 while having a cold and on some cold medicine is probably not the best idea. So that's going to cancel out, and I'm left with 40. which will be 25 plus 15. Yes, so the wheel has rotated pi over 2 through the Ferris wheel. So the co-height is 25 and the height is 40, so we're at the 3 o'clock position, and life is grand. Number 4, finally, it's not very useful to track the position of a Ferris wheel as a function of how much it has rotated. It would make more sense to keep track of the Ferris wheel as a function of time. Recall that the Ferris wheel completes 2 full turns per minute. Whew. So let theta equals 0 represent the position of car 1 at the bottom of the wheel. Sketch the graphs of the co-height and the height of a car as a function of time. So right here, we are at 2 minutes. And if we look at our Ferris wheel, we're at the ground. We're starting with car 1 right there. So we're going 2 times around in 2 minutes. That's correct, right? More likely, Ferris wheel completes 2 full turns per minute. Oh, for goodness sakes. 2 full turns per minute. So I'm going to draw that line. So if we look at the co-height, remember that's the distance, the horizontal distance. We're at 0. Okay, 1 minute, we should be back to 0. 2 full turns per minute. So sorry, at half a minute. So half a minute, we should be at 0, and another half a minute, we should be at 0. So this is half a minute. So at a quarter of a minute, we're up here. So at 0.25, we're also at a co-height of 0. So we're at 0.25. Let's write that down, 0.25 minutes. And we would also be back at 0.75 minutes. Back at 0. So 0.25, we're at 0. And then 0.75, we're at 0. Cool, so our co-height makes total sense. Let's draw a picture of our height. Remember, we're at 15, above the ground. So our midline is 40. So at time equals 0, we're at 15. At time equals half a minute, we're at the top. Not a half a minute, a quarter of a minute. Did it again. So 0.25 minutes and 0.75 minutes. So 0.25 minutes, we're at the top, which is right here. And then 0.75 minutes, we're at the top. Okay, we're back down to the bottom at half a minute, at 0 minutes, and then at 2 minutes, or at 1 minute. Goodness, why did they have to do 1 minute? All right, so that makes sense. We have our graphs, and we're good. The co-height and the height functions from part A can be written in our regular standard form. So just going from the graphs, identify the values of amplitude, omega, etc., etc. So from the co-height function, I have an amplitude of 25, and the height function I'm also going to have an amplitude of 25. Our omega, I'm going to pause for a second and come back to it. Our h value is going to be, if I take, hold on, if I take that circle and I'm dividing it into lots of pieces of the puzzle, lots of pieces of a pie, sorry, I'm actually going to go into eighths, and then our k is going to be equal 0. For our height function, Okay, we're going to translate that by 40. Our h is not going to change. So our omega, we're going to round this circle 2 times. So we have 2 pi and 4 pi. Our h is our phase shift. So that's the horizontal translation of the graph from the original sine function. So we're actually going to go to the right by 1/8. Let's go ahead and put them into our equations. Function of time, amplitude is good. Omega, oops. You remember we didn't translate anywhere vertically. Same amplitude, same shift, but we translated 40 degrees up. Okay, go to mode and switch your calculator back to function mode, and you can graph your co-height function and your height function, and you'll get the pictures shown here. Okay, it's a fun exercise. Explain the meaning of the parameters in your equation for x in terms of the Ferris wheel scenario. I'm actually going to start a new slide for this one, so hold on a second. Alright, for the co-height function, I wrote the equation here. You should have it in your notes already. We have the following. Our amplitude is 25. Our omega is 4 pi. H is positive 1/8, and K is 0. So amplitude is 25. Means that really the difference between the largest and the smallest values, the co-height is 50 feet. Because our maximum is 25, our minimum would be negative 25. So we now have the diameter of the wheel. The period, sorry, this would be the amplitude. The period is 2 pi over omega, and omega is 4 pi. So the period is 1/2. The frequency is 2. This means that the wheel rotates twice each minute. Cool? Another slide. I'm assuming you wrote stuff down from the last slide. So the phase shift is h equals 1/8. That's our phase shift. That just means that each quarter revolution takes 1/8 of a minute, which is 12.5 seconds. Without this shift, our equations would start car 1 in the 3 o'clock position. And that's not good. Okay, that's not reality. we want to start from the bottom. And lastly, the equation of the midline is y equals 0. That just means the co-height varies between 25 and negative 25 on the graph. Cool. Explain the meanings of the parameters in your equation y in terms of the Ferris wheel scenario. So I have y of t equals 25 sine 4 pi t minus 1/8 plus 40. Okay, a lot of these are going to be similar. Again, I have amplitude is 25, same as part E. The period is 2 pi over omega, which is 1/2. The frequency is 1 over pi, which is 2, same as part E. So go ahead and read that one. Phase shift is 1/8, same as part E. New slide. Here, the equation midline is y equals 40. Okay, which means the height varies and 65 feet. So we really just have 40, and we do a plus 25 up and a minus 25 down to get 65 and 15. Okay, in parametric mode, graph the functions x and y from exercise 3C on a graphing calculator. For 0 is less than or equal to t is less than or equal to 1/2. Sketch the graph. How is this graph different from the graph in exercise 3D? If you go back and look at exercise 3D, they look identical. The only difference is this graph has a different scale. For the parameter of t. Instead of needing 0 is less than or equal to theta is less than or equal to 2 pi, we use 0 is less than or equal to t is less than or equal to 1/2. Since the wheel makes one complete turn in 1/2 a minute. So that's our time. We do one complete turn in 30 seconds or half a minute. What would the graph look like if you graphed the functions x and y from exercise 3C for 0 to 1/4? Well, that is 1/4 of a turn. If we can do half a minute and do a full turn, then 1/4 of a minute will only be a half turn. Let me fix my mistake. Half turn in a 1/4 of a minute. Okay, evaluate x of 0 and y of 0 and explain their meaning in the context of the Ferris wheel. Hold on, let me write them down. Okay, there we go. Evaluated at 0, the x function is 0 and the y function is 15. All that means is when the wheel has not yet rotated, time is 0. We have not rotated at all. The co-height of the car is 0. So we're right here. The co-height of the car is 0, and the height of the car is 15. This means that the car is at the bottom of the wheel. Now let's evaluate x at 1/8 and y at 1/8 and see what happens. Hold on. So x evaluated at 1/8 is 25, and y evaluated at 1/8 is 40. Let's see what that means. So when the wheel has rotated for 1/8 of a turn, that means that it rotated through a quarter turn, since the wheel rotates every half a minute. So one full rotation is half a minute. This would be a quarter of a minute, and here would be 1/8 of a minute. So we're right there. That is rotated a quarter turn. So the co-height of the car is 25, because that is our radius. And the height of the car is 25 plus 15, which is 40. That means the car is at the 3 o'clock position, and we can see the distance of the car. Okay, exercises 6 through 9. Watch through this. This is something that is omittable if time is short, and I know the video's already been quite long, but this may help us complete our homework a little bit better. So, you are in car 1 and you see your best friend in car 3. How much higher than your friend are you when you reach the top? We're still using the same example from the previous example, where our diameter is 50 and we're 15 feet from the ground. So when you're at the top, your height is 65 feet, and you've rotated 180 degrees, which is pi. Your friend in car 3 has rotated through 60 degrees less than you have. I pulled the picture in to help us a little bit. So what we're saying is, let's just look that you're at the top in car 1, and your friend is in car 3, which is 60 degrees less than you have. So this right here is 60 degrees, right? So car 3 has rotated 120 degrees. 120 degrees is 2 pi over 3. I just changed it to radians. Using the height as a function of rotation, we can just do the math. So I'm looking at y, because that's the height of 2 pi over 3, equals 25 sine 2 pi over 3 minus pi over 2 plus 40. Go ahead and crunch the numbers using your calculator, and your answer would be 52.5 feet. You are 65 feet high, and your friend is 52.5 feet high. So 65 minus 52.5 feet equals 12.5 feet higher. Okay, the next two problems in your packet, we don't need to finish to be ready for your problem set, so we're going to bypass them right now just for sake of time. It was a tough lesson, but I know you guys will get it. It's going to be great. We'll do the problem set tomorrow in class. Good work today.